Maria Miss unmute ചെയ്യണം കേട്ടോ മൈക്ക്. മൈക്ക് അൺമ്യൂട്ട് ചെയ്യണം മരിയ മിസ്.
I am Maria Poulose, Research Scholar, Postgraduate and Research Department of Mathematics, Maharaja College, Ernakulam. My topic is random fractals. Introduction. Many objects in the nature can be created by applying the classical geometry like lines, circles, conic sections, polygons, and so on. In the nature, we can see clouds, tree, flower, broccoli, trees, fern, peacock, thunder, iris, brain, lungs. So these objects of nature cannot be modeled by applying Euclidean geometry. Hence, there is need to deal with complicated and irregular objects which can only be reconstructed by fractal geometry. What is fractal?
Slide മാറിയില്ല മിസ്. എക്സ്ക്യൂസ് മീ മിസ്. സ്ലൈഡ് മാറിയിട്ടില്ല. Okay.
Can you see it right now?
Yes. Introduction. What is fractal? Okay, കാണാം.
So, can you see it right now?
Yes.
So, these objects of nature cannot be modeled by applying Euclidean geometry. Hence, there is need to deal with complicated and irregular objects which can only be constructed by fractal geometry. And what is fractal? Mandelbrot took the word fractal from the Latin word fractus, meaning broken. He used it to describe sets that were too badly behaved for traditional geometry. Fractal is a set of self-similar objects. It is possible to copy the fractal several times on itself. Benoit Mandelbrot explained them as a geometric shapes that, when divided into parts, each part would be a smaller replica of the whole. The Cantor middle third set. Start with the unit interval 0, 1. Remove the middle third to get the closed interval 0, 1 by 3, union closed interval 2 by 3, 1. Continue removing middle thirds. The Cantor set C is what is left.
Excuse me, Maria Miss.
Yes.
PPT slideshow on അല്ല കേട്ടോ. ഫുൾ വ്യൂ കിട്ടിയിട്ടില്ല.
ഇപ്പൊ സ്ലൈഡ് ഷോ ആണോ?
അല്ലല്ലോ.
ഇപ്പോഴോ?
അല്ല. മിസ്സിനോട് സ്ലൈഡ് ഷോ ആണോ?
എന്റെ സ്ക്രീൻ.
ഓക്കെ, എന്തോ പ്രശ്നമുണ്ട്.
സ്ലൈഡ് ഷോ ഐ തിങ്ക് സ്ലൈഡ് ഷോ മാറ്റി ഇപ്പൊ സ്ക്രീൻ കാണാലോ അല്ലേ?
ആ, സ്ക്രീൻ കാണാം.
ഓക്കെ. Okay. So the Cantor middle third sets. So start with the unit interval 0, 1. Remove the middle third to get closed interval 0, 1 by 3 union, closed interval 2 by 3, 1. Continue removing middle thirds. The Cantor set C is what is left. So we have first the interval closed interval 0, 1. And we are removing the middle third of the closed interval 0, 1. You are getting the two lines. So that is the closed interval 0, 1 by 3 union closed interval 2 by 3, 1. So continue the removing the middle thirds. The candle set C is what is left. Okay. And the candle middle third sets. So in simple, E naught equal to closed interval 0, 1, E1 equal to closed interval 0, 1 by 3 union 2 by 3, 1. And C equal to intersection of all EI. Properties of the candle set C. So it is self-similar. The path of C in closed interval 0, 1 by 3 is scaled copy of all of C. It has details at all scales. It is simple to define but hard to describe geometrically. So its local geometry is strange. Every open interval containing one point of C must contain other points of C as well as points not in C. All fractals should have these properties. So one example is the von Koch curve. So begin with a unit line. We have replaced in second step, we will replace the middle third with the top of an equilateral triangle. Then replace the middle third of each of the 4 line segments. So the result is continuous. Nowhere we are continuing this procedure. You are getting the figure like this, and the result is a continuous nowhere differentiable curve with infinite length called the von Koch curve. And this is the complete von Koch curve we are getting. The next example, generalization of the von Koch curve. So you can construct the von Koch curve can be modified in a number of ways. The quadratic von Koch curve or Minkowski sausage. The next example is the dragon curve. So when you are repeating the procedure like this, you are getting the image like this. And this is the Mandelbrot set. Next, we are going to the dimension of a fractal. One of the main tools in fractal geometry is fractal dimension. So there are a lot of different ways to define fractal dimension. So Hausdorff dimension is the most widely used. So what the idea we are using is, look at covering the fractal with smaller and smaller sets. As the sets get smaller, we need more of them to cover the fractal. Measure how fast the number of sets increases as the size of the set decreases. So we can discuss that thing about the candle set. The consideration of candle set shows how to cover it with smaller and smaller sets. So we can cover C with first one set of, when we have a straight line 0, 1, one set of size 1, second 2 sets of size 1 by 3, 4 sets of size 1 by 9, etc. It's going on like this. So we are using the calculation. We can define fractal dimension as capital D equal to log n by log E, where capital N is the number of identical shapes and E is the magnification. So using this N and E, we are calculating the dimension of the candle set and we are noting that thing on a table. So in this table, you can see the values of E, values of D, and N is there. So in the first case, we have only E is 1 and N is 1. And in the second case, we are getting 3 and the N is 2 straight lines we are getting. That is N is 2. So log N by log E, that is log 2 by log 3 equal to 0.630929754. Then in the next stage, we have E equal to 9, N equal to 4. Therefore, the D equal to log 4 by log 9. So that is 0.630929754. So that is the calculation table we have find. So we want to measure how fast 2 raised to n grows relative to how fast 3 raised to minus n shrinks. So do this by looking at limit n tends to infinity 3 raised to minus nx 2 raised to n for different values of x. So fractal dimension of the candle set, we can write it as 2 into 3 raised to minus x, so equal to 1, that is 2 equal to 3 raised to x, or log 2 equal to x log 3, or x equal to log 2 by log 3. Therefore, the fractal dimension of the candle set is log 2 by log 3 equal to 0.6309. Suppose n delta is the minimum number of sets of diameter delta needed to cover the set F. We compare how fast n delta grows related to the how fast delta shrinks by looking at the graph. So it is showing how the shrinking and what happens, how fast the n delta grows. You can see from this graph. So by using this, why is this called fractal dimension? So it agrees with our ideas of what dimension should be. The fractal dimension of a point is 0. The fractal dimension of a line is 1. So and the fractal dimension of the candle set is 0.6309. The candle set had properties between those of a point and a line. It makes sense that the fractal dimension of the candle set is between 0 and 1. Then we are looking upon the fractal dimension of the von Kuch curve. So generalize the technique from the calculation for C. Again, the construction tells us how to get covers of the curve. So we can cover the curve with, first step, one full-sized copy of the curve. Then 4 copies of the curve scaled by 1 by 3. Then in the next stage, 16 copies of the curve scaled by 1 by 9. So etc. etc. 4 raised to n copies of the curve scaled by 3 raised to minus n. The diameter of the curve itself is 1, and so. So you can see the curve, and we have discussed the von Kuch curve, how we are constructing earlier. So we are writing all this one. The dimension of a point is 0. The dimension of the Cantor middle third set is log 2 by log 3 equal to 0.6309. The dimension of a line is 1. The dimension of the von Kuch curve is log 4 by log 3 equal to 1.262. 1.262. Then dimension of the Minkowski sausage is 1.5. The dimension of the dragon curve is 2. The cost of Britain. In one of his early papers on fractals, Mandelbrot addressed the question, how long is the cost of Britain? So this is a hard question in part because you get different answers depending on how much detail you include. So we are looking upon how we are finding this one. The cost of Britain. How long is the cost of Britain? Mandelbrot's answer was that the cost of Britain is a fractal, and so asking for the length is the wrong question. Instead, a better measurement is the fractal dimension, so which Richardson estimated to be 1.25. How long is the cost of Britain? So Mandelbrot's answer was the cost of Britain is a fractal. So that answer is wrong. The cost of the Britain is not strictly self-similar. So it varies randomly. It is stochastically self-similar. So there comes the importance of the random fractal. So we have already discussed about the fractal and examples of the fractal and how we are finding the dimension of the fractal, that is Hausdorff dimension, we have discussed the. So by saying that cost of Britain, it's clear that it is not possible to find that dimensions, that is we are using the random fractal is what we have to use. So actually the random fractal it is a set of statistically self-similar objects. We can get the same kind of stochastic self-similarity by adding an element of randomness to our construction. So we can look on the examples of random fractal. So we have already discussed the von Koch curve. So in the construction of the von Koch curve, if we are adding some randomness to that construction, then you are getting a random von Koch curve. So add randomness to the construction of the von Koch curve by flipping a coin to decide if each triangle we add should point up or down. So that is, if you are tossing a coin, if you are getting a head, so we can decide it as a triangle looking upwards. If we are getting the tail, we can decide it as the triangle looking downwards. So based on the coin tossing, we are deciding how the shape is going on. So that means in the construction of the von Koch curve, we are adding some randomness. So you are getting a random fractal. So this is one example of the random fractal. So when you are continuing this procedure, you are getting the random von Koch curve as this one. Now in the case of the candle set, we can include the randomness. So as we construct the candle set, flip a biased coin to decide whether or not to include each interval. So after starting with closed interval 0, 1. So include the interval if the flip gives heads. For example, if the probability of heads is 2/3. So we are giving that probability along with that candle set. So then we are getting the candle set like this. So you are not selecting all the lines when you are dividing and all those things. Okay. So like this, we are including the randomness to the candle set. Then you are getting the random candle set. And this applications of this random fractals mainly on modeling and characterization of natural forms and process to make predictions possible, and computer simulation of each phenomena to direct imitation of nature. So used in image compression, that is 6 times faster than JPEG. And antennas designed by fractal process have sensitivity at various frequencies. Human body is full of fractals. We have already seen the pictures, our iris, brain, all those things, lungs, all are of the fractals. So you can include that fractal math can be used to quantify, describe, diagnose, and cure diseases. So these are the main areas in which we are applying the random fractals. Using this, we can use, so it has application in computer science, also in the medical area also we can use the random fractals. So the references are like this: fractal geometry of the Kenneth, and then Bernard B. Mandelbrot, how long is the cost of the Britain, and a link is there, and a review on natural phenomena of the fractal geometry. It is an international journal of the computer applications. So that's all. Thank you.